Welcome everyone. We are going to discuss a very special integral today. And if you are here from the short, you know what the integral is. It is 0 to infinity sine x upon x dx. Now, why I say this is a special integral because this appears in many instances of physics in applied maths, and as you study higher physics, this integral keeps coming up. So this almost is taken as a standard result. And the value of this, as I have already revealed in the short and I will reveal in this video as well, is pi by 2. So this basically goes to pi by 2. It is curious because the integral of 1 upon x diverges while the integral of sin x upon x does not diverge. And interestingly enough, if you also do sin x upon x whole square, that is in fact also equal to the same integral 0 to infinity sin x upon x whole square dx. That is also equal to pi by 2. Well, that is fascinating actually. But this pattern does not really continue for long. From 3 onwards, the power 3, it becomes different. And we can also generalize it for any positive integer n. But that is going to be a bit tougher. So we'll focus on the basic integral, the fundamental one here. So how do we solve it? Well, one way to solve it is using contour integration, and that is using complex residues. But we will focus on real methods here. So define a function called f of a, and let this function be equal to 0 to infinity e to the power minus ax sin x upon x. And you have to say that a is greater than 0 and a is a parameter here. Okay, a is a variable. Let's consider a as a variable. We are doing this because we can prove that this integral basically converges and it is allowed to do differentiation under integral sign in this integral. That can be proved using the Feynman's theorem. And once we have that, we can differentiate both sides to get f dash a, which is 0 to infinity e to the power minus ax, and we are differentiating with respect to a, right? So minus x should be as a coefficient multiplied by sin x upon x dx. If you cancel off the x, you basically get the following integral 0 to infinity e to the power minus ax, and there's a minus sign outside, sin x dx. Okay, now what is this integral and how do we solve it? First of all, remember that sin x is the imaginary part of e to the power ix. If you do not know this result, this would be covered in the complex numbers video. And this is from the famous mathematical equation e to the power ix equals to cos x plus I sin x. Continue this to get minus imaginary part of. Now, inside you can write the whole integral. So what does the integral become? It becomes e to the power minus ax into e to the power ix. If you take minus x as the coefficient, this becomes a minus I dx. Okay. So, minus imaginary part of, and now what we do get is this. Since 0 to infinity e to the power minus any positive constant mx basically gives you 1 upon m, you can just do the indefinite integral and find out. This gives you 1 upon a by I. Multiply by the conjugate and stuff like that. You know how to find the real and imaginary part. So a plus I and a plus I you have to multiply on numerator and denominator. And what you would get is something like this: a plus I divided by a square plus 1. Well, the imaginary part is, of course, when you separate this and get the imaginary part is 1 by a square plus 1, right? So we get minus 1 upon a square plus 1. And that is the value of f dash a. Now, if f dash a is that, we can integrate f dash a to get f dash a dA equals to, remember that a is a parameter and that is why this is possible, dA upon a square plus 1. What does this get us? This gets us minus tan inverse a. That is the antiderivative of 1 upon a square plus 1. And on the left hand side, we get f dash a. The fundamental theorem of integral calculus tells us that obviously we can apply limits here as well. So the limits what we want to apply here is something like this. So we know that f of 0 is our required integral, right? Because f of 0 basically gives you sin x upon x. And if you do f of infinity or a tends to infinity, that basically gives you 0 because the first term here basically becomes 0. Okay, so we can do the limits like this: infinity to 0. Similarly here, infinity to 0. The fundamental theorem of integral calculus would tell us that this is equals to f0 minus 8 limit 8 tends to infinity f of a. And similarly here it would be so basically this would be not the integration. This basically would be like this because we have already performed the integration. This was just a writing mistake. Okay, like this. So minus tan inverse 0, which is 0, and then minus tan inverse of infinity, which is minus pi upon 2, because you know tan of pi by 2 goes to infinity. Also, we have discussed that this is 0. This means that f of 0 should be equals to pi upon 2, or in other words, sin x upon x, the integral of which from 0 to infinity dx should also equal pi upon 2. And that completes our integral. So, this is the result that we have been talking about, and now I also discussed about the result here about like the sin x upon x whole square and the generalizing it. So I really want you to give a try to this one first, and then you can also give a try to doing the generalized one, which is more useful of course, because you can basically put in the value of n and get any answer. But anyway, I will make a video on that as well later on. But if you like this one, if you like this explanation and the short, and you want to see more of this, please do subscribe. And if you can, please leave a like on this video and let me know in the comments. And I will reply to everyone. Thank you.